Hello, welcome back. In this segment, I will define the notion of well-formed proposition logic formulas. We have seen many formulas during this series on proposition logic. I wanted to give you some example of some proposition formulas that are arguably not well-formed. Okay, for example, if I give you P and Q or it's not really clear whether I should do P and Q first and then take R with it, or am I supposed to do Q or R and then perform a AND with P? So that's not so precise. Okay, we should be able to clearly define unambiguously what we mean by a formula, and that's the idea of well-formed formula. Okay, let's take another example, which is kind of rubbish, but to get across the core idea, I open a parenthesis, close a parenthesis, and then I put some connectors like implies, and then I put some variable P and Q. This is clearly rubbish. How can a computer recognize whether some formula is well-formed or something is not well-formed? So we need to formalize that logic more precisely. Suppose, let's assume we agreed that there's a finite set of proposition variables like P, Q, R, S, and so on. You may ask, what if I exhausted all the 26 alphabet letters? How can I define more variables? You can index the variables like P1, P2, P3, and so on. For the formal definition of well-formed proposition formulas, the only thing is we need a finite set of variable names. Okay. Let's make it simple. Let's just say we have variable names like P, Q, R, and so on. Let's say capital V is a set, not to be confused with the R notation. This is the capital V, which is basically set of all finite set of variable names that you would like to have. Okay. Each member in this set V is a logic formula. That's the very first definition of well-formed formula. Okay. So what about connectors like not and or? We have not used that yet. So we should think about them as well. So let's start with the simple connector, the not connector. Suppose you have pi as a formula. You can put a not in the front of that formula. This is also well-formed. Okay. You probably noticed that I have not used and, or, implies, equivalence, and so on. Those are all binary connectives, right? You need two things. So let's think about them now. Suppose you have established pi to be a well-formed formula, and let's say psi to be another well-formed formula. What it means is that, let's say pi, some binary connector. This can be an OR operator, can be an AND operator, or implies, or anything that we can use, equivalence and so on. Okay, so in this case, right, we need to put a parenthesis. So if you have pi as a well-defined formula, psi as another well-defined formula, pi with the operator and psi enclosed in parenthesis is also well-formed formula. So this is the third case. This is called inductive definition because we are defining well-formed formula using well-formed formula. Okay, you probably noticed that because when I said there's no need to put parenthesis for the not pi case, you may wonder why is that? Because if pi is made of, say, binary connectors, you would naturally put a parenthesis here, right? Suppose you have a formula as simple as A or B, you will be putting a parenthesis in the front of A and after B. Okay. And if you want to put a not for that, you already have a parenthesis. Therefore, you don't need to put a parenthesis here. That's the reason why you don't see a parenthesis for not pi. Okay. So the three things we learned: any variable is a well-formed formula, not of a formula is a well-formed formula. If you have two well-formed formulas, pi and psi, you can combine them to form a new formula with your operator, and you need to put a parenthesis in that case. All right. So let us now see this in action. dnfplayground.polyanklin.com. Okay, so if you wanted to know more about BNF, you can play it with yourself. Okay, it's called Backus-Naur form. Okay, so here is an example, right? Nothing to do with the proposition logic. Suppose you're modeling GPA, which is the grade point average in the US education system. in particular, where you would put grade in, for example, if you get a perfect score, usually it's 4.0, or it could be anything. It could be like a leading number could be, say, 3, and you got, say, trailing number to be 5, so you'd have 3.5 as a grade. How do you model this using BNF? So you create a variable called, say, GPA, and you're putting value 4.0. This is like other option, okay, or leading, the dot, and the trailing. So the leading itself is defined here to be any number between 0 to 3, including both 0 to 3. Trailing is similarly 0 through 9. Okay, we can actually compile and test it. That's interesting here. You can compile, all good. Let's say we wanted to start with GPA. Okay, let's select this as a GPA, and we put something. So first, let's put sensible things. 4.0. Yeah, it's a valid score. But 4.1 is not accepted. That should be the case, because the grammar says the leading digit can be only through 0 through 3. Yeah. All right. So this is the basic idea of this BNF. Now we will apply this idea for our case of propositional logic. So first thing I wanted to show to you is, I'll start simple, right? Create just only one variable. It may be a little boring, but let's get the idea across. Let's say the variable set V is just only one variable, P. So since V and R look similar, okay, I will choose some other variable. Let's call this alphabet, okay? So P is my only alphabet. And my formula now is slightly boring. It doesn't accept anything other than alphabet. Okay, let's create two variables then, at least a little bit more interesting. Okay, let's compile. Yeah, is it all good? It's all good, compiled. Now let's try to feed in a formula here. P, yeah, P is accepted. You see green. Q, yeah, accepted. But if you put PQ, it's not accepted, because you can't put two variables together just like that. The formula doesn't allow that. So the very basic case is every individual variable on your alphabet set is considered a valid formula according to propositional logic, well-defined formula. Now let's make it more interesting by introducing, say, let's say a not operator. Yeah. So not is basically, the tool doesn't allow me to use exactly the not symbol we followed. So I have to use like a tilde, for example. All right. So what is the next thing I need to do then? My formula can be just an alphabet, or I can have a not followed by my formula. Okay, this space has no meaning. Okay, this space has no meaning. So this is just for clarity. Okay, so we have form to be alpha, which is P or Q in this case, or not of a formula. Let's compile and run it. Okay, so we need to select the root tag, which is form. In that case, it's accepting. We get not P accepted as a formula. We can actually keep doing more. We can even put one more not. It will still accept. That's good. We are able to at least satisfy the not, but we cannot put this one. This is not acceptable, and the tool correctly detected it. So we're done with not part. Now let's think about the binary operator, the binary connectives, or like or, and so on, right? Let's do that. Or, and, implies. So again, implies, I'm a little bit cheating because the tool doesn't allow me to use the regular one arrow mark style. So I'm putting minus with the greater than symbol. Okay, these are the binary operators. You can add more like equivalents and so on, but for our purpose, this should be good enough. So we can actually use a formula, binary operator, and then another formula, right? That's the meaning of this, but we need to put a parenthesis according to the formal definition. So we need to put a parenthesis. So we need another, let me call it open, and a closed parenthesis means something like this. Okay, now we can say you need to have open parenthesis and you need to close it. Let's compile and see whether it compiles first. Yeah, it compiles. And now we can try something more complex. Say P and Q or R. Okay, I need to close it. So let's close it. I need to add an R as another variable. Let's see. Compile, everything good now. Okay. If you make a mistake, it catches you right away. I removed one parenthesis, it stopped me. And according to the definition we learned, P and Q, you may wonder why is this showing red? P and Q seems to be well-formed, but remember the definition said, if you have two well-formed formulas that you're connecting using, say, and or whatever, you need to put a parenthesis. So that is the reason why it is showing you an error. That's basically it. Okay, this is a little bit strict. The grammar is somewhat strict. I have not considered the case where you would like to have space between variables. Like it's difficult to read when I have, say, too many things together, right? There is no space. Let's say I wanted to put this. Now it becomes difficult to read. There is no space between the variables or connectors. How do you handle that? You can create your own variable for space and change the model to include space as part of your grammar. Okay.